this problem, we have an electron gun and it creates a beam of electrons moving with speed of 0.1 c. So that's V initial. We'll assume that the electron's coming down here close to the negative plate and it's moving forward with a speed of 0.1 c, or 0.1 times 3 times 10 to the 8 meters per second. It's moving through a parallel plate capacitor with a field strength of 50,000 newtons per coulomb. We see that the electric field points straight down. By how much does the beam deflect as it passes through the capacitor? And one other thing that we know is that the space between the plates is 0.5 centimeters. So let's think about what happens in this problem. As soon as the electron enters the electric field area, it feels an electric force. What do we remember about the electric force? Well, we know that the electric force is the charge of the electron times the electric field. So that's minus 1.6 times 10 to the minus 19 coulombs times the electric field. The electric field points down. This is a negative, so the electric force must point up. So then we ask, what is the path of the electron? So we have a little electron that's moving to the right, but it experiences a force that's downward, so it will carry on moving to the right as it moves upwards. So the force is up, it will get a motion in the upwards direction. As it moves up, it also moves right. So this is projectile motion. So this is going to be the path of the electron. And projectile motion problems we can solve using our kinematics. So let's make a list of the things that we know in our problem. So we can make a list for the information in the x direction and the y direction. So our initial position, so our electron starts right here and follows this path. Let's put our origin right here. Initial x position is 0, initial y position equals 0. Our final x position, we don't really know what that, as it goes through the capacitor, so our initial x is here, our final x is over here. Our final x position is 2 centimeters, 0.02 meters. Final y position, we don't know. That's what we're trying to sort out. How far does it deflect? How far does it move in the vertical? Our initial x velocity is 0.1 times c, so 3 times 10 to the 7 meters per second. Our initial y velocity is 0 because it's moving horizontally to start, the initial. Our acceleration in the x equals 0, and our acceleration in the y is something that we're going to find. So let's do that first. So we know that our acceleration in the y is equal to the force in the y direction divided by the mass, because F equals ma. We know that the force is the charge, or minus E times the electric field, and then that's divided by the mass. So then what we get is minus 1.6 times 10 to the minus 19 times our electric field, 50,000 newtons per coulomb, and our electric field is in the minus j direction. Divide that by the mass, 9.11 times 10 to the minus 31 kilograms, gives us an acceleration of 8.78 times 10 to the 15 meters per second j. So there's our acceleration in the y direction. So we want to find out how far does it travel in the y. Let's write down our equation in the y direction. So our equation in the y direction is that y final equals y initial plus v initial y times t plus 1/2 times ay times t squared. Ay we're good. Y initial we said was 0. V initial y is 0 because it moves horizontally. So we can find our y final if we know our t. Let's ask, can we find our t? So let's go back to the x information. We know it travels the length of the capacitor, which is 2 centimeters. We know that that horizontal speed is 3 times 10 to the 7. Let's use that to find our time. So x final equals x initial plus v initial x times t. So t is going to be delta x divided by v initial x equals 0.02 meters divided by 3 times 10 to the 7 meters per second. Put that through the calculator, we get a time of 6.67 times 10 to the minus 10 seconds. So there's our time. Let's substitute this into our y equation, and let's find that y distance. So y final equals 1/2 times the acceleration, which we already found thinking about our forces and field, multiplied by our time squared. Put that through the calculator, we get 0.195 times 10 to the minus 3 meters, or 0.195 centimeters. So we see that it deflects, it doesn't quite reach the plates, so it probably moves something like this as it goes through.